Welcome back to the deep dive. For months, we've been really getting into the weeds on the hardware, right? The physical stuff, the CPU, the RAM, all those circuits and gears.
Buzzing bits.
Yeah, exactly, the buzzing bits. But now, it's time to shift gears. We're moving up a layer to the magic, the invisible intelligence that takes all that chaotic hardware and actually makes it do something useful.
That's a perfect way to put it. We're going from the mechanics of the machine to the management of the machine. If you think about it, the CPU is the engine, and RAM is sort of the workbench, but the operating system, the OS, that's the boss.
The boss of the machine, I like that.
It's the executive, the central orchestrator.
And that's really our mission for this deep dive. We want to strip away all the technical jargon and show you, the listener, how this one piece of software connects everything, how it turns raw electricity into the apps you use every single day.
And this isn't just, trivia for tech nerds. The OS dictates everything. Performance, security, even just how you feel using your computer. If you don't understand the OS, you're only seeing half the picture.
Just a pile of expensive parts.
Exactly. A pile of very sophisticated but very confused inert components.
Okay, let's unpack this. To keep things straight, let's use an analogy. Imagine your computer is a massive, wild party.
Okay.
All the hardware, the keyboard, the screen, the hard drive, they're the guests. And they all want to talk at once, they all need resources, and it could easily turn into chaos. The operating system, then, is the ultimate party organizer.
Well, making sure everyone has a drink and nobody's double-dipping the chips.
Right. It prevents fights, makes sure the music is flowing, it manages everything so the party is actually fun.
And that organizational role it's fundamental. I mean, the sources we look at are really clear on this. Without that piece of software that boots up first, the hardware is just, and I'm quoting here, a bunch of confused parts sitting there.
It wouldn't even know how to turn on properly.
Not at all. No idea how to get input from a keyboard or put an image on the screen. The OS provides all that initial direction.
And while we think of, these polished desktops, Windows, Mac OS, this whole idea isn't new. The problem started basically as soon as computers got powerful enough to even think about doing two things at once.
Right. And if we connect this to the bigger picture, the first real operating systems started popping up back in the 1950s. Computers back then were these colossal, room-sized mainframes.
The giant ones with the spinning tape reels.
Those are the ones. And the OS was born out of really just pure necessity. These machines were so expensive you couldn't afford to have them sit idle for a second. So the OS was invented to help scientists and engineers share time on them efficiently. It wasn't about being user-friendly. It was about squeezing every last drop of utility out of the hardware.
Wow. So it's gone from managing one huge machine for a few scientists to managing billions of tiny tasks on the phone in your pocket.
The scale is just staggering. But the core functions are the same. Whether it's a huge cloud server or your tablet, the OS is there doing its three main jobs: bossing the hardware, juggling your files, and pulling off that magic trick of seamless multitasking.
That foundation is what makes our whole digital world work.
It really is. It's the essential layer. So let's start where the OS starts. At the very bottom, the invisible core that knows all the hardware secrets.
Okay, so every big organization has that one central part, right? The part that can't fail, that has to run everything. For the OS, that's something called the kernel.
And the kernel it's the absolute heart of the OS. It's this crucial piece of code that's always running, and this is the important part. It's the only part that talks directly to the physical hardware.
Directly. So my web browser can't just tell my Wi-Fi card what to do.
Nope. Never. Your web browser lives in what we call user space. It's like the public area of a building. The kernel, on the other hand, operates in kernel space, which is like the high-security control room.
Okay, so the user space is where my apps are.
Exactly. Your games, your browser, your music player. And if the OS is the party boss, the kernel is that super smart all-access assistant who knows every secret handshake with the hardware guests. It's got the master keys to the whole building.
And keeping those two spaces separate, kernel space and user space, that's what makes the system stable, right? It protects the important stuff from my potentially buggy video game.
100%. The applications can't touch the hardware. They have to ask the kernel politely. This process is called a system call.
A system call.
Yeah. So when you hit save in a document, your word processor doesn't write to the hard drive. It makes a system call, which is basically a formal standardized request to the kernel saying, hey, can you please save this data for me?
And the kernel checks its credentials, basically.
It does. It verifies the request, translates it into the low-level signal the hard drive understands, and then carries out the action. That mediation stops a rogue app from, say, trying to overwrite critical system files.
So it's a gatekeeper. What other kinds of low-level things is it doing all the time?
Oh, it's constantly busy. It's deciding where in RAM to put your programs. It's scheduling which process gets to use the CPU at any given nanosecond. It's managing all the basic input and output. When you save that file, the kernel isn't just passing a message. It's figuring out the physical location on the disk where those bits of data will live and making sure the file system knows where to find them later.
It's turning my abstract click into a physical change on a piece of hardware.
That's the perfect description. And because all the apps are constantly demanding resources, the kernel also has to be the ultimate referee.
Preventing digital fistfights.
Exactly. Imagine your email program and your music player both try to send sound to your speakers at the exact same moment. Without the kernel stepping in, you'd get garbled noise or maybe even a system crash.
A blue screen of death.
The dreaded blue screen. The kernel prevents that by putting the requests in a line, basically. It creates a queue, prioritizes them based on its scheduling algorithm, and makes sure one request is fully handled before the next one even starts talking to the hardware.
And that responsiveness, that millisecond-level decision-making, you can really see it in things like touchscreens. Our sources brought up this great example of a Kaurav, a student in India, using an Android tablet for educational games.
Yeah, that's a fantastic example because what the kernel is doing there is it's staggering. A touch screen isn't just sending data when you touch it. It's sending a constant stream of signals called interrupts to the CPU.
Interrupts, like a tap on the shoulder for the processor.
A constant high-speed tapping, thousands of them a second. And the kernel has to look at every single one and decide, is this important? Does the CPU need to stop what it's doing and pay attention to this right now?
So when Arav is drawing a circle on the screen,
The kernel is processing thousands of those interrupts, figuring out the path of his finger, translating that raw data into a shape, and then making system calls to the graphics hardware to actually draw the line on the screen. The fact that this feels instant, that there's no lag between his finger moving and the line appearing, that's a direct measurement of how fast and efficient the kernel is.
it's the boss making sure the most interactive parts of the party run perfectly no matter what else is happening.
Exactly, even with a graphically intense game running in the background.
That is amazing. So the kernel is the heart. Let's zoom out a bit and talk about the OS's broader job of managing all that hardware. Okay, so if the kernel is the core intelligence, the rest of the OS is out on the street making the day-to-day decisions. We know the CPU and RAM are crucial, but they're passive. They just sit there waiting for orders. This is where the OS puts on its reflective vest and becomes the traffic cop.
Yes, this is all about resource allocation. It's pure logistics. Think of your computer as a city. The data is cars, and the hardware components are the roads and intersections. Without the OS directing traffic, you'd have total gridlock, digital chaos.
So the OS is standing there with the whistle, telling everyone when it's their turn to go.
All the time. It's making these split-second decisions based on what's most important right now.
Okay, walk me through an example. Let's say I'm sending an email with a big attachment, but I'm also trying to watch a 4K video. How does the OS handle that?
Great question. So you hit send on that email. The OS immediately sees that and tags the process for your email client as high priority. It tells the CPU, hey, drop what you're doing and focus on encrypting and sending these network packets right now.
So the email gets priority.
For that moment, yes. But at the same time, you started that 4K video. The OS then talks to the RAM manager and says, I need you to clear out a big continuous block of memory. We need to buffer this video data so it plays smoothly.
And it's doing this on the fly.
Completely dynamic.
Uh.
It's constantly looking for memory that's not being used by other apps, reclaiming it and giving it to the video player. It's this continuous balancing act to make sure nothing stutters and all the parts are working together without crashing into each other.
But this gets even more complicated when you plug something new in, right? Like a webcam or a weird audio mixer. The computer doesn't magically know how to talk to it.
No, it doesn't. And that's where drivers come in. Drivers are these tiny, essential little programs, usually made by the company that made the hardware. Think of them as interpreters that the party boss hires.
Interpreters.
Yeah. Some of the hardware guests, like that fancy new graphics card, they speak a very specific proprietary language. The OS only speaks in general commands, like draw a circle or play this sound.
So the driver is the translator.
It's the critical translator. It sits in the middle. The OS gives the generic command, and the driver translates that into the precise low-level binary code that the chip on that specific piece of hardware understands. Without the right driver, the OS sees that something is plugged in, but it has no idea how to communicate with it.
Which is why sometimes you plug something in and it just doesn't work.
That's almost always a driver problem. The interpreter is missing or speaks the wrong dialect.
And this whole idea of managing resources super efficiently is even more important when you don't have a lot of resources to begin with.
Oh, absolutely. Look at the example from our sources about students in Brazil using affordable laptops, often running Chrome OS.
Right. Those aren't super powerful machines.
Not at all. They usually have less RAM and slower processors. So in that situation, the OS has to be an extremely strict traffic cop. When that student is in an online class, Chrome OS ruthlessly prioritizes. It gives almost all the CPU time to the webcam, the microphone, and decoding the teacher's video stream.
And it shuts down other things.
It basically puts them to sleep. Things like background file indexing, fancy desktop animations, they get almost zero resources. The OS is making a calculated decision to ensure that the core function, in this case, remote learning, works without stuttering, even on limited hardware.
That's a really powerful example of design choices. And for anyone listening who wants to actually see this traffic cop at work, there's a really easy way to do it.
Yep, you can do this right now. On Windows, it's called the Device Manager. On a Mac, it's in the System Report. It's basically the OS's internal checklist.
The manifest of all the guests at the party.
Perfect analogy. It's a list of every single piece of hardware the OS has identified and is controlling, from the tiniest internal chip to the gaming mouse you just plugged in. You're seeing the result of the kernel successfully finding and loading the correct driver for every component.
And if you see one with a little yellow warning symbol,
That means the traffic cop has found a car, a piece of hardware, that it doesn't have an interpreter for. It sees it, but it can't direct it. It's a fantastic, tangible look at the massive oversight job the OS is doing every second.
amazing. Okay, we've covered how the OS bosses the physical machine. Now let's get into how it manages all the information inside that machine. All right, so we're shifting now. We've talked about running the machine itself, but now we need to talk about organizing everything on it. Every photo, every document, every game. It's all just a file.
Yeah.
And in this role, the OS becomes a kind of super organized librarian.
It's much more than just putting files in folders. The librarian has to know the exact physical location of every single block of data on your hard drive or your SSD. It keeps a massive, detailed index so that when you double-click a file, it can be retrieved instantly.
And it also has to make sure that when you save something new, you don't accidentally write over something important.
Exactly. That's a critical part of its job. And the main tool the librarian uses for this is called the file system.
The file system. So that's like the Dewey Decimal System for a computer.
That's a great way to think about it. It's the specific methodology the OS uses to name, organize, and track all the files. It dictates how the data is physically arranged on the disk, how metadata is stored.
Metadata being things like the date you created it, the file size.
Right, all that information about the file. And different operating systems use different file systems, which are optimized for different things.
So they're not all the same.
Not at all.
Yeah.
Architecturally, they're quite different. Windows, for example, mainly uses NTFS. That stands for New Technology File System. Vary. But NTFS is known for being incredibly robust, can handle huge hard drives, and has a feature called journaling, which is really important. It basically writes down what it's about to do before it does it.
A to-do list?
Sort of. So if your computer crashes mid-save, the file system can look at that journal on reboot and recover your data without it becoming corrupted. It's built for stability.
Okay, so that's Windows. What about Apple?
Apple made a big switch recently to something called APFS, the Apple File System. It was designed from the ground up for modern flash storage, SSDs.
Which are much faster than old spinning hard drives.
Way faster.
Mm-hmm.
And APFS is built to take advantage of that speed. It could do things like create instant snapshots of your entire system. That's why backups and system restores on a modern Mac can feel lightning quick. It's the file system's architecture.
And what about the third big player, Linux?
Linux generally uses file systems like XT4. XT4 is valued for its sheer rock-solid stability and reliability. It's been tested for years in demanding server environments where the machine absolutely cannot go down. So it's the choice for tinkerers and for the massive servers that run the internet because it's proven and open.
So beyond just knowing where a file is, this librarian also has to act as security, right? It handles permissions.
Permissions are fundamental, especially on a computer that has more than one user. The librarian puts digital locks on all the books and shelves. It determines who has the right to read a file, who can write to it, meaning modify it, and who can execute it or run it as a program.
So my kid's account can't delete my work documents.
Exactly. The OS enforces that separation strictly. It's what prevents a normal user from accidentally deleting a critical system file that the OS itself needs to run. It's all about protecting data integrity and user privacy.
Let's apply this to a mobile device. I mean, we don't really see the file system on our phones, but it's there.
It's absolutely there, and it's working overtime. Take the example of Yuki, a student in Japan using her iPhone. Her phone's OS, iOS, uses that super fast APFS. This means she can pull up her school notes, which might be buried deep inside an app almost instantly.
And it's also managing her backups, right?
Right. When a phone backs up to iCloud, that's the librarian doing its work. It's not just a dumb copy. The file system is efficiently tracking which files have changed, encrypting them for security, and making sure that a safe, secure copy is stored off-site. So if she loses her phone, her data isn't gone. It's all managed seamlessly by the OS.
And these different philosophies, robustness for Windows, speed for Mac OS, stability for Linux, that's kind of why they all feel so different to use.
It's a huge part of it. The underlying architecture shapes the whole experience. Windows feels solid and compatible with everything. A Mac feels snappy and fluid, especially for creative work. And Linux feels powerful and customizable.
Which leads to that great example of the kid in Africa using Ubuntu.
Yeah, Ubuntu is a popular and free version of Linux. Because it's open source, the user has incredible freedom to customize it. So this kid can download fun themes, change the entire look and feel of their desktop, and really make the computer their own. That's not just cosmetic, it's empowering, especially in places where paying for software isn't an option.
Okay, so the librarian keeps everything tidy. But the real magic show is multitasking. We just don't do one thing at a time anymore. I mean, right now I have a dozen browser tabs open, music is streaming, and a file is probably syncing in the background. The OS makes that feel completely normal.
It's a total illusion. A brilliant one, but an illusion nonetheless. In this role, the OS is the circus juggler. It's tossing all those applications the balls in the air and switching between them so incredibly fast that it looks like they're all in the air at the same time.
But really, the CPU can only do one single thing at any given instant.
One thing at a time. The magic is how the kernel scheduler switches the CPU's attention. It's called context switch, and it happens millions of times a second.
So how does it decide what to work on? How does it schedule everything?
Okay, so first we have to understand the units of work. Each running application is what we call a process. A process is like its own little isolated world. It has its own dedicated chunk of memory that other processes can't touch.
So my web browser is a process.
Correct.
Yeah.
And inside that process, you have smaller units of work called threads.
Threads. Okay, so what's the difference?
Think of it this way. If your browser is the process, one thread might be responsible for rendering the web page you see. Another thread is handling the network connection to download images. And a third thread might be playing an animated ad in the corner.
Got it. So they're all mini jobs within the main job.
Exactly. And the kernel schedules these individual threads. It might use a method like round robin, where every thread gets an equal tiny slice of CPU time. Or, more likely, it uses priority scheduling. It knows that the thread playing your video is more important than a thread doing a background spell check, so it gives the video thread more slices of time.
And the context switch is the moment it jumps from one thread to another.
That's the one. And it's a very delicate operation. The OS has to save the exact state of the current thread, all its data, where it was in its calculation, and then load the exact state of the next thread.
This sounds like it takes time, like there's overhead.
There is. And minimizing that overhead is the secret sauce of a good kernel. Modern CPUs have special hardware to make this context switching super fast. But the goal is to switch so quickly that even though your low-priority task is only getting a little bit of attention here and there, it still makes progress. And your high-priority task feels perfectly smooth and responsive.
And this whole system, with processes in their own little isolated worlds, that's a huge safety feature.
It's the most important safety net, because each process has its own protected memory. If one application freezes or crashes...
The dreaded spinning beach ball.
Right. If that happens, the OS can just terminate that one process. It can remove that one rowdy guest from the party without the whole house coming down. The other applications, and most importantly the kernel itself, just keep on running completely unaffected.
You know, it's a pretty good metaphor for how to manage our own lives.
It really is. The machine is a master of prioritization. The OS knows that streaming audio is more important in the moment than backing up a file. As learners, you can apply that same logic. You prioritize the homework that's due tomorrow over the video game you want to play. It's about allocating your limited resource time efficiently.
The OS as a productivity coach. I love it. Okay, we've gone deep on the invisible stuff, but for most of us, the OS is the thing we actually see and click on. So yeah, all this background work is amazing, but the OS needs a way for us, the humans, to tell it what to do. And that's the user interface, or UI. It's basically the boss's smiling face.
It is. It's the desktops, the icons, the menus.
Ah,
It's the entire visual and interactive layer that translates our clicks and taps into those complex system calls we were talking about.
you click the trash can icon.
And the UI translates that simple action into a formal request to the file system to delete the underlying data. It's the bridge between human intention and machine execution.
And we mainly interact with two big types of UI, right?
Broadly speaking, yes. The first, and the one almost everyone uses, is the graphical user interface, the GUI.
The GUI.
Yep, it uses all those visual things, windows, icons, pointers. It's designed to be intuitive. It's like ordering from a picture menu in a restaurant. You just point at what you want. Windows, Mac OS, your phone's screen, those are all GUIs.
And what's the alternative? The one that looks like a 90s hacker movie.
That would be the command line interface, or CLI. You access it through a terminal, and you interact by typing very specific text commands.
So instead of a picture menu, you're giving the chef a detailed recipe.
In Latin, maybe. It's much less intuitive and has a steep learning curve, but it's incredibly powerful, precise, and easy to automate. The vast majority of the world's servers are managed entirely through command line interfaces for that reason.
And with phones taking over the world, the UI has had to become simpler and more accessible than ever. The touch interface is king.
It is. And that's a huge deal for global inclusivity. Think about that example of a kid in Kenya using a cheap Android tablet. The UI has to work flawlessly with touch. That means big, clear icons and a system that responds instantly to a swipe or a tap.
And it has to do that even if the internet connection is spotty or the processor isn't very fast.
Exactly. The boss has to be friendly and accessible to everyone, regardless of their technical background or the quality of their hardware. That's a core principle of good mobile UI design.
And of course, we love to personalize that smiling face. We change our wallpapers, add widgets.
That customization is a key feature. It lets you arrange your digital workspace in a way that makes sense to you. It lets you solve your own organizational problems.
Which brings us back to that try this at home idea. You can actually use the OS's tools to build your own system.
Totally. When you create your own folder system, like My Digital Party, with subfolders for school, games, and projects, you're engaging in the same kind of hierarchical thinking that the OS librarian uses. You're tailoring the system to fit your brain, and that's a huge step towards being more efficient.
Okay, so all OCs do these same core jobs, but they do them in very different ways. It's time to actually look at the big families of OCs and why you might pick one over another.
Right. The three big desktop families, Windows, Mac OS, and Linux, each have their own philosophy. Windows is by far the most popular. Its strength has always been its incredible backward compatibility and its massive support for hardware and software, especially for gaming.
It's the jack of all trades.
It is. It's built to run on a huge variety of hardware from countless manufacturers.
Then you've got the Apple ecosystem.
And macOS is the polar opposite, in a way. It's a proprietary system that only runs on Apple's own hardware. Because Apple controls both the hardware and the software, they can hyper-optimize the OS.
So it's a tailored suit instead of an off-the-rack one.
Perfect analogy. And that tight integration and optimization have made it the go-to platform for a lot of creative professionals, like video editors and musicians.
And then there's the quiet giant, Linux.
Linux is fascinating. It's free, it's open source, and it's incredibly modular. While some people use it on their desktops, its real strength is behind the scenes. It powers something like 90% of the world's cloud servers, most of the world's supercomputers. It is the workhorse of the internet.
Because it's so stable and secure.
Stable, secure, and gives system administrators maximum control. It's built for heavy lifting.
And of course, we can't forget the mobile cousins, Android and iOS, which have completely changed the game globally.
Mobile OASs are a special breed. They're designed around one huge constraint that desktops don't really have. Battery life.
Power management.
Extreme power management.
Yeah.
They're designed to be incredibly aggressive about putting apps to sleep, throttling in the CPU, and managing all the little sensors to sip power as slowly as possible.
And we should definitely hit that fun fact again. Android is actually built on top of the Linux kernel.
That's right. You can think of Android as the fun, user-friendly cousin of Linux. It inherited that rock-solid kernel, which is a big reason it's been so successful and can run on such a massive variety of phones and tablets all over the world.
Billions of them. From a farmer in Vietnam checking weather apps to a student in Canada playing games.
That's the scale of it. The underlying Linux architecture supports that huge diversity.
And in today's world, it's not enough for these systems to just work on their own. They have to work together.
That coordination is key. Take that example of a family on a trip in Europe. Dad has a Windows laptop, mom has an iPhone. For them to seamlessly share photos, the two different operating systems have to speak the same networking language.
TCP/IP.
Exactly. The Windows OS manages its Wi-Fi connection, the iOS device manages its connection, and they both adhere to universal standards so they can communicate. It allows these two totally different bosses to coordinate a group activity without any problems. Hashtag tag C, the critical importance of updates.
We've got this picture of a super organized, efficient boss. But even the best boss needs new tools and training. Let's talk about something people love to ignore. OS updates.
Oh, this is so important. People see that update available notification and just hit remind me later for weeks. But updates are the single most critical maintenance you can do.
They're not just about getting new emojis.
Not at all. An OS update is the boss getting new tools, but more importantly, it's patching holes in the building's security.
So what's actually in one of those updates?
Three main things. Number one, and the most urgent, are security patches. Hackers are always finding new vulnerabilities. When a company like Microsoft or Apple discovers one, they rush to create a fix. The moment they release that patch, the secret is out. Every bad guy in the world now knows about that vulnerability.
So if you haven't updated, you're a sitting duck.
You're leaving the front door wide open with a sign on it. That's the most critical part. Second, you get bug fixes. No software is perfect. Updates fix little glitches, prevent crashes, and generally make the system more stable.
And the third thing ties back to our hardware discussion.
Yep, it's updated drivers. A big OS update will almost always include a fresh batch of optimized drivers from hardware manufacturers. That update might make your Wi-Fi faster or your graphics card more power efficient. It's free performance and stability improvements.
So how do companies like Apple and Microsoft get people to actually install these things?
Well, they've moved to a more structured cycle, like Patch Tuesday for Windows. And for really critical security flaws, they will often push a forced update. The OS will basically nag you and maybe even slow things down until you install it, because an unpatched machine on a network can be a risk to everyone else.
So it's the boss insisting on a mandatory safety drill.
You got it. And the process is pretty much the same everywhere. You check for the update in your settings, you download it, you install it, which almost always requires a restart, and then you verify that you're on the new version. It's a necessary cycle. It teaches you that digital health requires continuous maintenance.
The machine teaches us that you can't stand still. You have to keep improving. Okay, we've established the OS as the manager. But in the world we live in now, it also has to be the primary defender. It needs to be a bodyguard.
Absolutely. The security features are baked into the core architecture of a modern OS. It's acting like a party bouncer, checking the ID of every program that tries to run, every piece of data that comes in from the network, and making sure nothing malicious gets inside.
We know about firewalls, which block bad network traffic, but what are the more advanced tools the OS uses inside the system?
Two really powerful concepts are sandboxing and virtualization.
Sandboxing, tell me about that.
Sandboxing is all about isolation. The OS takes certain applications that are high risk, like your web browser, since it's constantly accessing untrusted stuff from the internet, and runs it in a restricted environment, a sandbox.
So it's like putting a potentially rowdy party guest in a separate, walled-off room.
That is the perfect analogy. If your browser gets infected with some malware, that malware is trapped inside the sandbox. It can't escape to see your personal files, it can't modify the kernel, it can't infect the rest of your system. This is a fundamental part of security on iPhones and modern Android phones.
Okay, and what about virtualization?
Virtualization is even more extreme isolation. It allows the OS to run an entire separate simulated computer, a guest OS, on top of your main OS. Security researchers use this all the time. They can download and test a suspicious virus inside a virtual machine, and if it completely destroys the guest OS, it doesn't matter. Their real computer, the host OS, remains completely untouched.
And we mentioned earlier that Linux has a kind of special reputation for security.
It does, and it comes from its open source roots. For one, its architecture is built on a very strict separation of user privileges. By default, you don't have root or administrator access, so it's much harder to accidentally damage the system.
And the second reason?
The community potluck idea. Because the source code is open for anyone to see, there are millions of expert eyes all over the world constantly auditing it for flaws. When a vulnerability is found, It's often spotted and patched by the community incredibly quickly.
But no matter how good the OS bodyguard is, some of the responsibility still comes down to us, the user.
It's the final and most important layer. The OS gives you the tools, the firewall, the sandbox. But it's a team effort. The best security in the world can't protect you if you are tricked into turning it off, or if you click on a suspicious email link and enter your password. Smart digital habits are the ultimate defense.
All right, last big job for the boss. It doesn't just manage the party inside the house. It's in charge of connecting to the massive world party that is the internet.
That seamless ability to just hop on a Wi-Fi network, that's all the OS. It manages the physical hardware, like your Wi-Fi card. It handles the security and passwords. And most importantly, it manages the entire TCP/IP protocol stack.
The what now?
TCP/IP is just the fundamental language of the internet. The OS handles all the low-level grammar of that language. It's what gets your computer an IP address. It's what translates a web address like google.com into numbers the network understands. And it's what breaks down all your data into little packets to be sent out and reassembles them when they arrive.
So when I watch a YouTube video, the OS is reassembling thousands of tiny packets in the right order.
In the right order and delivering them to the right application, your web browser. It's a huge invisible logistics operation.
And it has to manage the quality of that connection in real time, especially for something sensitive like a video call.
Oh yeah, it's constantly calibrating. Take that example of the girl in Australia video calling her grandmother in the UK. Her OS is monitoring that connection every millisecond.
Looking at latency, bandwidth.
Exactly. And if the connection starts to get shaky, the OS makes a decision. It might tell the video app to slightly increase the video compression to use less data, or it will prioritize sending the audio packets over the video packets, because choppy audio is much more disruptive to a conversation than a slightly blurry image.
So it's making these quality of service decisions on the fly to preserve the human experience.
All to make sure the connection feels as clear and stable as possible, even when the underlying network is struggling. It's the traffic cop's international duties.
An amazing bridge from our little box to the entire world. Hashtag, tag OTRO, synthesis, and final thought. What a journey. From a pile of inert silicon to this incredible organizational powerhouse. We've seen the OS as the traffic cop mastering the hardware, the librarian organizing our data, the juggler making multitasking possible, and the bodyguard keeping us safe.
It truly is the essential middle layer. It connects back to the hardware, managing every single clock cycle, and it connects forward to our apps, giving them a stable and secure platform to run on. Without it, none of this works.
Here's where it gets really interesting for me. This entire system we've described, this rigid, rule-bound, highly organized framework, that's the world that every creative piece of software has to live in.
That's right. We've shown how the OS makes the computer an adventure by enforcing these strict rules for stability and efficiency.
This raises an important question.
Now that we understand the boss of the machine, right? It's strict memory sandboxing, it's permission controls, it's rigid scheduling for CPU time. How does that structure both enable and constrain the creativity of the apps built on top of it?
What do you mean constrain?
Well, what if a brilliant developer has an idea for an app that needs to do something truly new, something that requires accessing hardware in a way the OS currently forbids for security reasons? They hit a wall built by the OS. What amazing new kinds of computing, what radical new app functionalities are we unknowingly missing out on because of the necessary rules the party boss has to enforce?
So how are our favorite apps shaped not just by what they can do, but by what the OS won't let them do?
Exactly. Think about that. The limits of the OS might just be defining the limits of our digital world. And that's the next frontier of our adventure.
A perfect provocative thought to end on. Thank you for joining us for the deep dive. We'll catch you next time.